So this is the slide that we ended at, and it's partial melting and the resulting magma composition. So the other day we discussed partial melting and how certain minerals melt at certain temperatures different from other minerals. So when you take ultramafic mantle rocks and you partially melt them, it's going to create a mafic magma, because mainly the lower temperature or felsic minerals are the ones that are melting and then rising up into a magma chamber, and then perhaps even erupting out of a volcano. So then when you partially melt mafic ocean crust, you're going to end up with intermediate magma. And then when you partially melt intermediate lower continental crust, it's going to give you felsic magma. We'll take out the word lower just to avoid any confusion, but it's like the lower part of the continental crust that's closer to the mantle. But that's going to give you felsic magma. So the summary is that magma is always less mafic and therefore more felsic than the original rock that it originated from because of partial melting. Because the entire rock does not melt all at once to form the magma. You're always only melting first the minerals that melt at a lower temperature. So those are the felsic minerals. So then we're going to talk about classification of igneous rocks and identification of igneous rocks. And this is going to help you when you get up to the igneous rocks lab, when it comes time to identify igneous rocks in the lab. So when you classify igneous rocks, you take a look at the texture and the composition. So igneous rock textures, the word texture here is not really the same as when you're talking about texture in everyday life. We're not really discussing things being like rough versus smooth. When you're discussing igneous rock textures, it's referring to the size of the mineral grains or crystals. In this case, the word grains is crystals. Okay, so we're looking at like the size of the crystals in an igneous rock. Also, we look, are there air bubbles in the rock? Or is there a lack of crystals? In the case of natural glass, volcanic glass, you would have no crystals at all. Okay, so those are the things that we're looking at for rock textures when it comes to igneous rocks. So the grain size, as we discussed a little bit previously in this same lecture, the grain size depends on the cooling rate of the magma or lava. And a summary is that magma that cools and crystallizes slowly beneath the surface, or intrusive igneous rocks, can take thousands to millions of years to cool and crystallize. So because it takes a long time for the crystals to form, there are going to be larger crystals and they're going to be visible because they're large enough for us to see them. In contrast, lava that cools quickly above the surface, or extrusive igneous rocks, may take months or years to cool. That's going to be if the lava flow is thick, it'll take a longer time, but it's still pretty fast compared to the plutons forming underground. Okay, you see like the contrast between months and years compared to thousands to millions of years, okay? So because this is a quick or short cooling time, you're gonna form either tiny crystals or no crystals at all. So the rate at which the magma or lava cools is going to give you different grain sizes. So here is a list of various igneous textures that we're going to discuss. And I have them color coded based on if they're intrusive or extrusive. And then you have a third category, which combines two different cooling rates. So we have phaneritic, that is related to coarse grains or visible grains. Pegmatitic is very coarse grained. Aphanitic is fine grained. Vesicular is air bubbles or gas voids. Glassy is no mineral crystals. Pyroclastic or fragmental is referring to volcanic ash that gets solidified. And then porphyritic is when you have coarser and finer grains together in the same rock.
So that one's like two rocks, two like separate rocks?
It's in the same rock though. Like within the rock, it's kind of, you could think of it like two different types of rock, but in the same rock.
Okay.
Yeah, and then so the top two is plutonic or intrusive. And then the this purple color in the middle is volcanic or extrusive. And the pink on the bottom has two different cooling rates. So then I'm going to go into the details of each of them. But this is just a diagram from your book where it shows you examples of phaneritic textures on the right and aphanitic textures on the left. So if you can see the rocks on the right, you could see the crystals, and the rocks on the left, you can't really see the individual crystals. I mean, you can a little tiny bit, but for the most part, you can't really see the crystals. And then they also divide it by composition. So like the top two are felsic, then the middle one, they're intermediate composition, and the bottom two are mafic. So when I said here, for classifying igneous rocks, it's related to texture and composition. So composition we discussed earlier in this lecture, the felsic, mafic, and intermediate. Okay, so phaneritic textures are coarse grained, meaning you could see it with your eye. You don't need a magnifying lens or a microscope. And this texture is related to slow cooling of magma underground. The minerals have plenty of time to grow large as the magma cools slowly. So an example would be this rock called diorite. Pegmatitic texture is when mineral grains in the rock are at least 1 centimeter across. Typically, pegmatitic texture rocks have a granitic or felsic composition. And they form if the magma had high water content or increased fluidity or low viscosity, because then the atoms are able to move around easily within the magma. So if they're able to move around easily, then they're able to grow and add on to crystals that are already forming, like the nuclei that are forming. So you're able to get larger crystals. So here's an example of a pegmatite rock where the crystals are quite large. So this white piece here, this whole thing is a crystal. Then you have this like grayish piece in the middle, that's another crystal. And then this piece on the left is another crystal. So these crystals are quite large. And this is an example from Orchard Beach, which is in the Bronx in New York. And this was this large pegmatite. It's a little difficult to see in the photo, but there were large crystals in there. So rocks that have a pegmatitic texture are called pegmatite. Like that's the rock name, is a pegmatite. Aphanitic texture is a fine-grained texture where you need a magnifying glass to see the mineral crystals. So here, like you see this rock basalt, the crystals are very tiny. You don't really see them just by looking at the rock. Aphanitic texture is going to result from rapid cooling associated with lava flows. So these are extrusive rocks, where the molten rock cools quickly, solidifying before the mineral grains are able to grow larger. Then we have vesicles, or a vesicular texture. So vesicles are air bubbles or gas voids in rocks that form from gaseous lava. So gases that were dissolved in magma underground will start to bubble out of the molten rock as it reaches the Earth's surface as lava. Because the gases are no longer under pressure, as you go away from being deep underground, going closer to the Earth's surface, the gases are under less pressure from the surrounding rock that was putting pressure. So this is going to allow the gases to start bubbling out of the molten rock. And then the molten rock hardens and solidifies while the gases are bubbling out. So you end up preserving the gas bubbles as this vesicular texture. So this would be like opening a new bottle of soda and then instantaneously freezing the soda. You would end up with like a lot of air bubbles in the frozen soda. And here is a photo of a rock with vesicular texture, and this was taken on the William Patterson campus. And sometimes those gas voids or air bubbles sometimes have minerals that will form inside, and those are called amygdals. So here is an amygdal that formed inside this air bubble. This rock is also from William Patterson campus. So then another texture is glassy texture. This is related to natural volcanic glass. This is going to be a shiny, glossy rock that breaks with conchoidal fracture. Conchoidal fracture means it breaks along smooth, curved surfaces. Glassy texture rocks form when lava cools very quickly and is too viscous for atoms to move around to bond with each other and form mineral crystals. So there is no crystallization that has occurred and no mineral crystals are present in this rock because the atoms were unable to bond with each other and form crystals. Then we have a pyroclastic texture. This is also called fragmental. This type of texture is associated with explosive volcanic activity. Rocks composed of consolidated ash from volcanic eruptions describes what a pyroclastic texture rock is. So it's mainly just consolidated ash, but then you also have like these little glassy fragments, little pieces of volcanic glass. So if the fragments in a pyroclastic rock are small, we call it tuff, T-U-F-F. If the fragments are larger, then we call it volcanic breccia. And this is an example of the volcanic ash that gets spewed out of a volcano. So then when this ash falls to the ground, this is all very hot. It's like hot volcanic glass and ash, which is like tiny pieces of volcanic glass, sort of, very, very, very tiny pieces. So when all of this material falls to the ground, it like solidifies together. And that's what gives us the pyroclastic igneous rocks. And then I have this, this picture here of volcanic ash. So this is just a quick video of the ash being spewed out of a volcano. Okay, so it is pretty, it was a little bit grainy. So if you want to watch the original video, it should still be there. Okay, and then that brings us to a porphyritic texture, where mineral crystals of obviously different sizes are in the same rock. So you have phenocrysts, which are your larger minerals. Usually those are all going to be the same mineral type within the rock. Excuse me. Then the ground mass, or the matrix, has the smaller minerals. The ground mass can be either fine-grained or coarse-grained, or phaneritic or aphanitic. So it could be either, depending on the rock. So these rocks have a complex cooling history where they have two different cooling rates. And then the rock name is going to use the word porphyry along with the description based on the composition and the texture of the ground mass. So for example, andesite porphyry. That little box here will help you later when you're identifying the rocks, when we do the igneous rock lab. So how do porphyritic textures form? Step one, this is cooling rate number one. So you have a magma chamber deep underground, and the magma starts to cool. So the high temperature minerals at the top of the Bowen's reaction series are going to begin to form, and then they're going to grow large because the magma is cooling at a slow cooling rate deep beneath the Earth's surface. So for example, a mineral called amphibole is going to form while the rest of the magma remains liquid. Okay, and that goes back to what we were talking about. When a magma cools, you start to form some of the crystals while the rest of the magma still remains liquid. So then step two, if the magma chamber were to rise closer to the surface of the Earth, the rest of the liquid magma is going to then cool at a faster rate because it's at a cooler temperature closer to the Earth's surface. So when the magma cools more quickly now, it's going to form smaller crystals than those that already formed in step number one. So then your larger crystals are called your phenocrysts, and then the rest of the rock is going to be smaller crystals, and that is your ground mass or matrix. Now, the ground mass, again, I said before, could be intrusive or extrusive. So it could be fine-grained or coarse-grained, depending on the situation. So if this magma chamber were to like go really close to the surface and even erupt as lava, then the ground mass would be fine-grained. But if it stayed down here, but just closer to the Earth's surface, you would have small crystals, but that were visible, but they would be smaller than the phenocrysts. So porphyritic rocks can form, again, with either an aphanitic ground mass or a phaneritic ground mass. And like a lot of things in geology, I use food examples. So when you have the aphanitic ground mass, it sort of resembles a chocolate chip cookie. So like you have the chocolate chips, which are the phenocrysts, and then the rest of the cookie, you don't really see like grains in there. It just kind of looks like a smooth texture with like nothing, no like crystals visible, right? So the only like things that you see in this rock are the chocolate chips, right? The rest of it's just like a solid color background. If the matrix or ground mass were phaneritic, meaning coarse-grained, that resembles more of an oatmeal raisin cookie. So you have the raisins, which are the phenocrysts, and then the rest of the cookie, the ground mass, you see the oatmeal pieces in there. But the oatmeal pieces are smaller than the raisins. Okay, so I think of the porphyritic rocks kind of like cookies. Okay, so that brings us to the volcanoes part of the lecture. So a volcano is a hill or a mountain that forms around a vent where lava, pyroclastic materials, and gases erupt from beneath the Earth's surface. Most volcanoes form in areas where tectonic plates meet. Those areas are called plate boundaries. So this figure shows you volcanoes of the world. Most volcanoes, again, are shown at plate boundaries. Convergent boundaries are where plates are colliding into each other. And that's shown as like this dark red line, that's convergence. And you see volcanoes is the red triangle. So where you have the dark red convergent line, you have a lot of volcanoes. And then the lighter orange color line is for divergent plate boundaries. That means that the plates are moving away from each other. Now this map mainly shows volcanoes on or near land. So like the mid-ocean ridge has volcanoes, but they're not shown as triangles on this map. But then when you go to Iceland, which is on the mid-ocean ridge, you do have the volcanoes showing as red triangles. There were two major volcano belts. You have the circum-Pacific belt, which is also known as the Ring of Fire. 60% of all active volcanoes are on the circum-Pacific belt. And that's around the Pacific plate, the tectonic plate. Then you have the Mediterranean belt, which is 20% of all active volcanoes are located there. Most of the rest of Earth's volcanoes are near or at the mid-ocean ridges, which are underwater volcanoes that form where tectonic plates move away from each other. Some volcanoes are at hot spots, which are not related to plate boundaries. For example, Hawaii. So here's a map of the Ring of Fire, and it includes Central and South American volcanoes, the Philippines, Indonesia, Japan, and New Zealand, the Aleutian Islands in Alaska, and the Cascade Mountain Range in Northern California into the southern British Columbia area. Volcanoes led to the creation of much of the Earth's early atmosphere and hydrosphere through the process of outgassing. And we talked about that in the first lecture, if you want to refer back to that. And volcanoes led to the creation of ocean crust. Volcanoes also create what we call volcanic islands through the process of forming volcanic island arcs, which we will discuss when we do plate tectonics. Major volcanic eruptions can also have profound short-term effects on climate. For example, Mount Pinatubo in the Philippines erupted in 1991 and had short-term global cooling effect from the ash ejected from the volcano, and it went up into the atmosphere and it blocked some sunlight. So we had a short-term cooling effect worldwide from that volcanic eruption. It just lasted a couple of years, the cooling period. It wasn't long-term at all. So what can come out of a volcano? You can have gases, lava, and pyroclastic materials. So let's first go over volcanic gases. Volcanic gases include 50 to 80% water vapor, and then also carbon dioxide and carbon monoxide, nitrogen gas, sulfur dioxide, and hydrogen sulfide as well, which are dangerous. Volcanic gases can be dangerous in general. So the sign here in the photo says, volcanic fumes are hazardous to your health and may be life-threatening. Now, expanding gases can also help propel lava out of volcanoes, similar to how if you were to open a bottle of soda after shaking it, the gases are going to expand pretty quickly when you open that bottle. And the quick expansion of the gases will cause quite a bit of the soda to actually squirt out of the bottle as well. So the same thing with volcanoes that have a lot of expanding gases. You're going to have like a lot of volcanic materials, mainly lava, are going to spew out of the volcano. Also, the gases lower the viscosity of the lava, allowing it to flow more easily. So here is a photo of a volcano, and there's gases coming out, including water vapor, carbon dioxide, and sulfur dioxide. And then here is a vesicular texture in an igneous rock because of those gases expanding, bubbling out of the lava, and then the lava hardens and turns into a vesicular rock. Okay, and the second thing in the list of things that come out of a volcano was lava. So we're going to discuss the types of lava that can come out. So there were two different types of lava flows. A lava flow is just the lava that flows out of the volcano, and it describes how it flows along the ground. So we have pahoehoe, which is going to be a flowy, ropey looking lava flow, and that's related to less viscous lava. It almost is going to look a little bit like taffy. And then you have what's called lava flows, which are jagged and angular, and those are more viscous lava. Or those are related to more viscous lava. So here is a pahoehoe lava flow. So it looks kind of ropey and flowy. Here's the ropey looking lava flow of Pahoehoe. And then you have an A'a flow over an older Pahoehoe flow. Okay, so this is a GIF of an A'a flow. So you can see it's lava that is piled up kind of high, and that's because it is viscous.
So that one like crumbles, Professor, and the other one's like a ropey type thing?
Yeah, you could think of it like that.
Okay.
Yeah. Yeah, this is a lot more, it's a lot thicker. So it like piles up and it becomes more of like jagged edged. Yeah, it looks a little bit more crumbly. And actually on the bottom of this is an older Pahoehoe flowy, ropey looking lava flow. So it just depends on the viscosity of the lava at the time. And viscosity could be related to the temperature as well as the composition. And then this is an example of an A'a flow, and you can see it's almost like a wall of lava piled high, and lava moves pretty slowly. It's not like in a movie where you have lava flowing really quickly, like chasing after people. It's more of a slow moving process.
I have a quick question.
Yes.
How are they able to stand that close to that type of flow of lava? Aren't they going to get their lungs? Aren't they going to be like contaminated with all of the pyroclastic debris and all of the chemicals that come out of that lava?
Well, in this particular case, it doesn't look like there's pyroclastic materials nearby, but there are gases coming out of the lava, and it is going to be pretty hot. But yeah, this picture always makes me wonder what's happening. Like, did they walk up to the lava to get the photo shoot? Like, I don't know what is really even happening here, right? Like, did they walk
Maybe
up?
photoshopped.
I don't think so. I think this picture is older than Photoshop.
That's some good Photoshop if it was, but yeah, they had to like hold their breath or something. Because I'm also thinking about the temperature. The temperature would, like incinerate their lungs. Like it's interesting how they even got that.
Yeah, it is. It's going to be pretty hot in this area. They probably only walked right up here and then came back for the photo, like it, turned around to take the photo. I'm not really sure the details, but it is kind of an interesting photo that does make me wonder what's really happening here. But yeah, so you do see the gases and it is going to be pretty hot, and they probably should not be breathing in while they're standing so close. Yeah. So then what type of lava flow do you think this is? So this photo is from the book, and it looked like a good photo to just kind of wonder, like, what is that lava flow? So do we think that's an A'a flow or a Pahoehoe flow? I see an answer in the chat.
A'a flow?
What? I'm sorry?
The A'a flow?
Yes, and I do see that in the chat as well. Yeah, so like someone said earlier, it looks kind of crumbly. So the A'a flow is going to have a crumbly look. I like that description. Thank you for bringing that up a few minutes ago.
You're welcome.
And yeah, so this kind of has that crumbly, rugged look. So yeah, that is the A'a flow. Then we have something called columnar jointing. So this is a pattern of how mafic lava cools and contracts and then cracks. Keep in mind the word contract means to shrink. So sometimes mafic lava, when it cools and shrinks, it cracks into hexagonal shape, columns. So this is columnar jointing. So you can see on the top picture, you have these columns. That's an older mafic lava flow that cooled. And then the pile in front of this wall of columns is columns that broke off and just fell down and left a pile here. So these are like broken columns. And then this bottom picture here is in top view. So if you were to walk on the top of this lava flow, rocks here, you would see, unless, I mean, it looks like there's grass covering it, but if you were able to see the top of the columns here, it would look like this. And it just happens to form hexagon shaped columns. And then here's a diagram showing what that looks like. Now, when we're discussing mafic rock, we're mainly talking about basalt in this case. So a local example of columnar jointed rock is the Palisades sill. So if you were going to drive from New York into New Jersey on the George Washington Bridge, you are facing the Palisades sill and you are able to see the columns. So this is a local example. This is a not so local example in Northern Ireland called the Giant's Causeway, where you could see the hexagons and then you could see the columns here. And then we're back to another local example. This is columnar jointed basalt on the William Patterson campus. This is near the tennis courts, which is right near the science building, actually. So this is columnar jointed basalt. And this tells us there was an ancient volcanic eruption of mafic lava on the campus of William Patterson University. So that's pretty exciting. We have columnar jointing on the campus. Yes, later in the semester when we're able to go outside, if we have let's say a day with nice weather, we will be able to take a look at these. Okay, then related to lava flow, we also have something called pillow lava or pillow basalt. So this is non-explosive eruptions of mafic lava that occurs underwater. Much of the upper part of the ocean crust is actually pillow lava. And it's basically lava that chills beneath the water as it oozes out of a vent. And it actually forms like pillow shapes. So it's like these blobs of lava that cooled underwater. I kind of think of this being like a tube of toothpaste. If you were to squeeze toothpaste out of the tube and freeze it instantaneously, you would get like a blob of frozen toothpaste. So it's sort of a similar concept where you have lava like squeezing out from the ocean crust under the water. And as it touches the cold water, it hardens. So it's a similar concept, right? You got like this squeezed out lava and it hardens. So that's how you get these blobs, okay? So just imagine a tube of toothpaste, you're squeezing the toothpaste out and freezing little blobs of toothpaste. Now here is a local example of pillow lava. This is in the Orange Mountain basalt in Patterson, New Jersey. So this indicates that there was lava erupting into a body of water. And this is actually one of the pillow lavas right here, this blob here. When we do plate tectonics chapter, we'll get into more detail about why there were volcanic eruptions in the area around Wayne and Paterson, New Jersey. We'll discuss why there's basalt and pillow lavas. Okay, so the third type of material that could come out of a volcano was pyroclastic materials on that list of 3 types of materials. So pyroclastic materials are ejected solid materials, including volcanic ash, which is particles less than 2 millimeters, lapilli, which is material 2 millimeters to 64 millimeters, and volcanic bombs, which are greater than 64 millimeters. Now keep in mind, 64 millimeters is 6 centimeters, 6.4 centimeters. And volcanic bombs are a twisted and streamlined shape because they form as blobs or globs, whichever word you like better, of lava are ejected out of a volcano, and then they solidify and harden as they fall to the ground. So it's almost going to be like a water droplet shape that hardens and solidifies as it falls to the ground. So this is a picture of a volcanic bomb. Okay, so again, think of it like a water droplet, like a raindrop that forms into a raindrop shape as it falls and then hardens. Okay, so the blobs of lava are hardening as they fall, so they end up having this shape. And then here's the lapilli and the ash. And here is a photo of ash covering all of this area in Washington State following the eruption of the Mount St. Helens volcano. And that happened in May of 1980. So it looks like snow, but it's not. It's all ash. It's volcanic ash. And you could see here they're wearing masks, which today is not so uncommon for us because of COVID. But they're wearing masks because there is ash in the air and they don't want to breathe it in because volcanic ash is kind of sharp. It's like little tiny shards of glass, but they're very, very, very tiny. So it's not really safe to breathe in volcanic ash. So that's why they're wearing masks. And then I have a video of volcanic bombs coming out of a volcano. Okay, so here's a video of, here's the video of the volcanic eruption showing the bombs coming out. Okay, so that again was the recording of a volcano in Iceland that had volcanic bombs and also a lot of pyroclastic materials like ash spewing out. So then we're going to discuss the different types of volcanoes. You have shield volcanoes, cinder cone, and composite cones or stratovolcanoes. And then that's related to felsic versus mafic lava. Different lava compositions are associated with different types of volcanoes. So basaltic lava has a low viscosity, so it can flow long distances. So that's going to be related to wide, big volcanoes. And then intermediate or andesitic lava is too viscous to flow far, and it tends to break up as it flows. So you're going to get not as widely extensive volcanoes. Okay, so shield volcanoes are wide, low, rounded profiles. They look similar to like a superhero's shield. Okay, that's kind of where the name comes from. It looks like a shield that's lying down on the ground. Shield volcanoes are made of basalt or mafic rock. And they form because the mafic lava flows easily and it flows far. So you're going to get a wide, gently sloping volcano. Now, these are gentle eruptions with a lot of lava, but you don't really have a lot of pyroclastic materials exploding out of these types of volcanoes. An example of a shield volcano would be in Hawaii. Okay, you have the Mauna Loa volcano, for example. Okay, so Hawaii is made up of shield volcanoes. Then cinder cones are small volcanoes built mainly from pyroclastic materials such as ash that were ejected from the volcano, and they accumulate around the vent. So these are cinder cones. And then gases in the lava expand rapidly, so you get explosive eruptions. Lots of pyroclastic material. This 400-meter high cinder cone named Paricutin formed in a short time in Mexico in 1943. So pyroclastic materials began to erupt in this farmer's field. And then there was some lava flow related to it as well, which covered 2 nearby villages. And then all of the volcanic activity from this particular volcano ended by 1952. So it was not a long-lived volcanic activity coming from this cinder cone. Here's another cinder cone. This is near Flagstaff, Arizona. So most of the material making up this volcano is pyroclastic material, and then you do have some lava related to it, but it's mostly pyroclastic. Then we have composite cones or stratovolcanoes. These are steep-sided volcanoes composed of pyroclastic layers and lava flows. The rock type formed related to these types of volcanoes is called andesite, which is an intermediate composition. These are going to be violent, explosive, and dangerous eruptions. This photo here is Mount Fuji, a composite volcano in Japan. It last erupted in 1707. And then this is a cross section of what a composite cone or stratovolcano looks like. These words are interchangeable, okay? They're just 2 different words for the same thing. And then here's another picture and another diagram of a composite or stratovolcano. So you do have pyroclastic material and lava involved here. Whereas the cinder cone is mainly pyroclastic materials, and the shield volcano is mainly lava. This is Mount Shasta in California. That was another example of a stratovolcano. This is a size comparison of the 3 types of volcanoes. So a shield volcano is the top picture, very, very long and wide, extensive volcano. That again is made of mafic lava or basalt gentle eruptions with lots and lots of lava. Then you have your composite cone, which is a lot smaller. And then you have your cinder cone. The composite cone is the stratovolcano or the composite volcano. Okay, and then your cinder cone is a lot smaller than the other two. Then we have pyroclastic flows. These consist of ash, volcanic glass, and other fragmental debris, and the material is rapidly propelled from the volcano. And this is very dangerous. So you see this pyroclastic flow is going down the side of the volcano. And then also you have wind that's pushing the pyroclastic material. They erupted further up into the atmosphere. And then you have ash fall, which is the ash falling down. So an example of how dangerous a pyroclastic flow can be is Pompeii, Italy. So in the year 79, Mount Vesuvius erupted, and there were deadly gases and pyroclastic flows that killed many people in the village of Pompeii. So it could be very deadly. Then you have intraplate volcanism, which are volcanoes that are located far from any plate boundaries, or in other words, they're in the middle of a tectonic plate. So magma from the upper mantle can rise to the surface in blob-like masses called plumes. Areas where this occurs are known as hotspots. So mafic lava from the ocean crust builds basaltic shield volcanoes. For example, the Hawaiian Islands built as the Pacific plate moves over a hotspot. Some hotspots are in the middle of continental crust, for example, Yellowstone National Park, and in that case can produce felsic magma. And that rock type would be called rhyolite. So here's what a hotspot would look like. So here you have a plume, which is just a blob of magma that's rising upward. And here is the ocean crust, and some of those blobs of magma are rising up through the ocean crust, and they lead to the formation of a volcano. But the ocean crust is still going to be moving in this direction in this example because plates move, tectonic plates move around the earth. So this plate is moving to the left. So this is an older volcano that's now extinct. It's no longer over the ocean hotspot. So these are older volcanoes. And sometimes over time, they start to sink down, and sometimes they're no longer above the water surface. Okay, and then here's your young, new volcano that's still forming. And then here is a different diagram showing a similar concept, but here's Hawaii. And here's the Pacific plate movement is that direction. So you get a line of older volcanoes like this. Okay, so again, it's the same concept, just different diagrams showing you the same thing. So here is the volcano that's still forming over that hot spot. Here's the direction of plate movement, and here are extinct volcanoes. So those are no longer able to erupt. So here's Hawaii. This is like the young volcano here. And then these are the older Hawaiian Islands. And then you have the Emperor Seamount chain, which is even older. So Hawaii like this island of Hawaii, is 0.7 million years old to the present. So it still erupts every once in a while. And then you have this island, which is less than 1 million years old. This island is 1.3 to 1.8. This is 2.2 to 3.3. And this island is 3.8 to 5.6 million years old. Okay, so these are the older islands. They are no longer over the hot spot, so they're no longer erupting. This is still over the hot spot, so you still have eruptions. Then we have Yellowstone National Park. Yellowstone National Park is a hot spot. It is in the middle of the North American tectonic plate. And it is a hot spot with a whole big magma chamber underneath the ground, but not really, really, really far deep underground. It's in some areas a little bit closer to the surface. So that allows for some magmatic activity and some heat to affect the surface of the earth there. So you do have some lava. In this case, it formed rhyolite in some of these areas. And over here you have basalt. This is your rhyolite magma chamber. This deeper down is your basaltic. And these form from partial melting. Again, the mantle is ultramafic rocks. So when you partially melt the ultramafic rocks, you're going to get basalt magma. Excuse me. And then when you partially melt your basalt, you're going to get more felsic, which is rhyolite. And then you have hydrothermal fluids, which are hot fluids related to the hot magma underground. And in some cases, that leads to hot springs. So Yellowstone has hot springs, and it has, in some areas, every once in a while, you have the blacktop that makes up roads that go in and out of Yellowstone National Park. Sometimes the blacktop like melts. So there have been times where some of the roads leading into the park have been inaccessible because like the blacktop starts to melt because you have the magma underground. So again, it's not that deep underground, right? So it is sort of able to affect the surface. But yeah, I thought that story was pretty interesting when I heard it, that occasionally the roads melt a little bit leading into the park. So that brings us to the end of the igneous rocks and volcanoes lecture.